3215 fits in. Today, though, Alex Meaney used to be with RightSoft. Now he's with Meaney HVAC. Actually, I don't want to introduce you, Alex. Go ahead and introduce yourself. Let folks know who you are. This guy knows more about HVAC than I'll ever know. So go ahead. The floor is yours, sir. I'll let you introduce yourself. Tell us who you are and what you know.
All right. Yeah. So I was the trainer for RightSoft for close to 20 years. It was just a couple months away from 19, 3 months away from 19 years when I left. We were purchased a while back with by a big old Berkshire Hathaway company, Warren Buffett money, and the money got better, but you couldn't do anything quickly, right? Everything took forever. It's big corporate stuff. It just didn't agree with me. So I've gone out on my own as a private consultant, trainer, designer, whatever. Most of my focus is on teaching people to do good quality HVAC design. My preferred tool for that still RightSoft, right? And no bad blood there on either side. At least I hope not. As far as I know, they're still pretty friendly with me. In fact, they were my first customer. So yeah, most of my time is spent teaching HVAC contractors how to design a good system, how to design a proper system, and also teaching mostly HVAC contractors, not exclusively, building science. There's a ton of overlap between the world of HVAC and building science. We were just talking about it before the meeting, Jason and I, about if you're installing HVAC systems and you're not well educated, if not an expert in building science, you're vulnerable, because it doesn't matter whose fault it actually is. When there's a comfort issue or an air quality issue, who gets the finger pointed at, right? And so I teach everything from how to do a manual J load or pick a system correctly or design a duct system to how to do pressure differential diagnostics and blower door tests and duct leakage tests and things like that. I'm certified to perform those kinds of tests. I am not yet certified to teach them. So I usually just sort of cover the basics and how they can help their business. But yeah, that's, and occasionally I do design work for people, but like I said, my focus is typically on training. So usually when I'm doing design work, it's what I call assisted design, where a designer or contractor or whoever who is actually doing the design will do it with me, and I'll show them what I'm doing and explain why as that happens. Also going to be launching a video subscription site that teaches the same stuff that I've just been talking about, because there is kind of a lot, right? When you want to learn the basics, when you're starting at zero and you want to get yourself up to the level of skill that should be average anyway. That currently that might be a lower bar than we want, but there's a lot to learn there, and doing so while paying by the hour is not always feasible. So I'm trying to create a tool that allows people to do that in a more economic way. So there's going to be a video subscription and then regular live streams, kind of like this, except maybe a little more interactive, hopefully.
Wow. So are you going to use YouTube? Have you decided on a platform for the video?
It's probably going to be my own site. It's probably going to be something on meanhvac.com. Because I think I'm going to use Vimeo, because YouTube has some limitations, right? It's not going to be free, unfortunately.
Gotcha. Right.
It's I'm giving away too much of the milk there.
well, there's plenty of folks willing to pay for it, and frankly, if you're good at it, which you are, and you do the work, which you will, why in the world shouldn't you be paid for it? I certainly appreciate you doing this for us for free. And Reese asked, will this presentation be recorded? I'm assuming so. It will be recorded, Reese, and it will be for free on our YouTube channel, but hopefully that'll get some of these HVAC contractors to bring Alex down here to Texas and train their guys up. But it will be available on our YouTube. And then also for your ICC CEUs, yes, there is ICC CEUs for this. Just fill out, as always, fill out the course evaluation from Kathy, and she'll get you your CEUs. Back to you.
Yeah.
Sorry about the interrupt.
That's actually the what inspired me to do pre-recorded work and subscription pricing is not, as many people assume, the desire to have recurring revenue on very little work. It was my time filled up so fast that taking random phone calls and doing things like this, that aren't for pay and just for the love of the game, as it were, within like 2 weeks became like impossible.
Right.
And so, and I've been in situations where I have close friends in the industry who are consultants who I've, given a lot of free advice to over the years. And when I needed to ask them for some, they wanted to have me pay them money. I didn't hate that. Right. When my electrician buddy comes over and helps me helps around the house and, whatnot, I pay him. But at the same time, I didn't want to be asking for people for money in those situations. So, right. So that's going to be the approach there. So we got a full house, you think?
We're ready to go. 72.
Right. Cool. Rock and roll. That's a good number. All right. Okay, so ladies and gentlemen, welcome to Building Science Whack-A-Mole, HVAC and the law of unintended consequences. So we're going to be talking about how a lot of the good things we do can cause bad things to happen. So first things first, want to get this out of the way. Good things are good, right? We like having more efficient systems. We like saving money on energy. We like going green. These are not bad things. The point of this presentation is not by any means to say that having high efficiency systems and improving our code are things that we don't want to do, right? The good outweighs the bad. Okay, good things are still good. It's just you have to be aware of the unintended consequence. You got to be aware of what happens when you do these things, right? So we're going to talk about some big picture trends. We're talking about some other tiny detail stuff too as we go. We're getting tighter and tighter buildings. There are a lot of things that go along with that effects that happen. Better and better insulation. Smaller buildings are becoming. It's one of those things where the average building size was shrinking up until COVID, and I'm just putting a giant asterisk on everything COVID. Right. Everything changed very, very drastically. I don't know what's going to happen when the supply chain rights itself. But I think it's safe to say that operating off the pre-2020 trends might still be a way to go. And even post-COVID, the average house footprint has increased in size, but the median hasn't. So that means the big houses that we build are getting bigger, and the small houses that we build are not getting smaller. They are getting more numerous, but it's averaging out to something more in the middle. But we are building more of the small houses, so that is still something that is happening. Townhomes and multifamily homes are still gaining in popularity. High efficiency equipment is a big thing. So I don't know how many of you guys have background in HVAC, but the changes that are coming through with HVAC equipment to keep up with our efficiency standards they're significant and they have consequences. Tied to the tighter buildings is the need for more ventilations, and I love this. It's great, but the efficiency improvements we're making in the retrofit marketplace, that's where we can really see some issues that get us burned. Again, still talking big picture. Issues of scale are one of the reasons why we have problems with this. Things are happening when we just literally shrink the size of stuff because we don't always have a great understanding of what the impacts are of changing the scale of things, mostly due to geometry. There's such a thing as linear, square and cubic, right? You have linear feet and square area and cubic volume. And those things increase at different rates when you change size, right? Cubic volume changes faster than square footage changes faster than linear feet. And it can cause issues the way those things interact. There are a lot of things in the world now that are offsetting each other that we don't know about, right? The example I like to give to building science people is the whole white roof thing. Remember that? Let's all paint our roofs white. We'll save on energy bills, and we'll turn our attics into mold factories. Shoot. And so there are certain forces that are opposing each other that make things work some of the times, and we upset that balance. This one is one that I'm sure frustrates you a lot. Cherry picking and half measures, right? We write this nice building code, and then people get their hands on it, especially when we have selective enforcement, right? And we start, okay, well, we're going to enforce that. My favorite was, and I saw a little bit of this in Texas. We're going to make you put ventilation in the house, but we decided that doing blower door testing was too expensive. So yeah, great. That's a wonderful idea. Let's build a leaky house and then add more outside air to it, right? And that's just half measures kicking in. Narrowing tolerances. This happens a lot with HVAC equipment, right? The more precisely we engineer things, the less wiggle room we have, and that can hurt us. Lagging indicators would just be way too much of, and I think this is every industry, but I can really speak intelligently about the HVAC side of things. Way too much of the HVAC industry is reactionary, right? I could have told you, any expert could have told you 5 years ago that we were going to need some 1-ton air conditioners and heat pumps on the marketplace by now, probably by several years ago, in fact. And so far, if you're not buying one from Mitsubishi or like one or two other mini split manufacturers, they're still not available, which is it's criminal. But it's because we're reactionary, right? It's because we wait for the demand to exceed what it would cost to start supplying. Bystander effects. This is really fascinating field of study in psychology and sociology. It's the somebody else will do it effect, right? You may have heard of Google Kitty Giovesi. It's a woman who got attacked, with everybody in New York had their windows open and heard it, and nobody called the police, right? Somebody else will do it. There's a lot of that happening in our industry. So to illustrate scale problems, because scale problems are probably the most significant issue that we have. As we change the size of things, we have an impact. I like to ask, it's like the old joke or the old riddle. I don't think you can call it a riddle. It's kind of a joke. It's a prank you play on people when you ask them what's heavier, a pound of feathers or a pound of bricks, right? And of course they're both a pound, right? So there's no answer to that question, but you watch people say it's a pound of feathers all day. I like to say, what's larger, a degree of heating or a degree of cooling? The answer is a degree of cooling. For real. Effectively, right? Now, in reality, they're both 1 degree, right? In reality, they are both the same unit of energy, and they contain the same amount of energy. One degree of heating, 1 degree of cooling. Whether you're adding heat or subtracting heat, it's the same amount of energy. Now, you could argue that with latent, you're probably getting some condensation going along with it, but the way the question's asked, they are the same. But when you're talking about building science, when you're talking about HVAC, you're not talking about pure temperatures, right? You don't talk about pure degrees. Talk about temperature differences, okay? And if 95 degrees is a hot day, and I know you're in Texas, 100 degrees is a hot day, 105 degrees is a hot day. Let me do some easy math in my head, right? We're going to say it's 95. If 95 degrees is a hot day, that gives you, and you're trying to shoot for 75 degrees in the house, that gives you a 20 degree temperature difference. So every degree of that is 5%. Okay. You change the temperature by 3 degrees, you are having a 15% impact on the temperature differential, which is what actually matters in load calculations. Well, we'll just keep it to load calculations. It's what matters in cooling and heating is what matters. On the heating side, if 20 degrees is a cold day, and yeah, most of your climates aren't hitting 20, I know, but if 20 degrees is a cold day, like I said, nice round numbers, and 70 degrees is the target indoor temperature, that's a 50 degree temperature difference. That means every degree of difference is 2%. Change things by 3 degrees, that's a 6% difference, not a 15% difference. And so when we scale things, right, and when we look at things, we don't always look at stuff like that. We don't always look at things in context, right? We look at it as, oh, that's 1 degree of difference. We don't say, well, how does that actually impact things when you run it through the machine, right? And that's what you got to watch out for, right? So Our first big talking point, and I did not tailor this presentation for Texas, but I did happen to cherry pick a Texas location for our example. This is the case of the incredible shrinking loads, right? As we improve our code, we are reducing the load on the HVAC system. Great. Problem is we're reducing the sensible load faster than we're reducing the latent load. And that throws things out of balance, causes some problems, right? So to demonstrate this effect, I ran a load calculation on a typical 2,400 square foot house in Austin, Texas. Okay, and I used typical building materials from the late 80s to the 90s to in every couple of decades, and then I did a few that exceed code today, right? Things that you might see in green building programs for Energy Star and things like that. And what we see here, right, this white line is the cooling load. That's the total cooling load, and it's dropping. And so is the heating load. And the thing about Austin, Texas is the temperature difference for heating and cooling is pretty similar, actually, which is why these lines are sort of riding down together, right? Cooling dropped faster at first because we were under insulating our attics and our windows. But once we got that straightened out, things started to sort of fall evenly. What has changed the most in this process is the relationship to sensible and latent. Now, if you don't know, and I should have led with this, I apologize. Sensible and latent are the two different kinds of cooling, right? In cooling, you have two jobs. You have to control the temperature, you have to control the moisture. So sensible is the energy you use to control temperature. Latent is the energy you use to remove moisture. If you're always getting confused or can never quite remember that, you heard it, but it's always like, which one's which? Here's how you remember that. When you make things cold, the temperature drops. That makes sense, right? Well, there you go. That's sensible, right? Temperature dropping, that's sensible. You make things colder, temperature drops, that's sensible. Latent is the hidden energy use. Latent means hidden, right? And so you make things cold and some moisture comes out of the air, doesn't affect the temperature, but you're using that energy. That's the hidden energy being used to remove moisture. So the relationship between those things is often called the sensible heat ratio. They're actually going to be calling it the sensible heat factor. There's one of my little feathers in my cap. I helped rewrite the Manual S. Was on the working group these last couple of years to create the new Manual S, and I hope to be on a few more of those committees that rewrite some of those code books. And one of the things that this actually didn't come from me. This is the brainchild of Kimberly Llewellyn over at Mitsubishi.
I love Kimberly.
Yeah, absolutely. She's the best. And Kimberly pointed out that people constantly get confused between the sensible heat ratio of the building load and sensible heat ratio of the equipment capabilities, the capacities. They're not the same thing. And it's very easy to confuse them because we both call them the sensible heat ratio as if it's like one number when it's two distinct numbers. So going forward, we're going to call that ratio between sensible and latent, or sensible and total is actually the ratio. Sensible heat factor when we talk about the load, and we're going to call it the sensible heat ratio when we talk about equipment. And so when I look at the this load calculation here, the sensible heat factor is 0.89 and 0.9. So I'm just going to round that and call it 0.9. In the older homes, right? Meaning on a design day, okay. Oh, wait. Yes, sorry. I was looking at my wrong. I looked at my preview slide for a second. Yes. On a design day, 10% of the energy was needed to control moisture. Okay. And in the early 2000s, 10% of the energy was needed. Starting in the 2010s up to today, 14% of the energy is needed to control moisture. That's a big jump, right? That's a 40% increase when you think about it, right? Yeah, okay, it's only 14%, but it's a 40% increase from what it was. That's a big deal. This is where we're sitting right now. Now, as we build homes better, as we start to exceed code, you know what's happening here? Because you start to see this go back up a little bit, right? Doesn't get back up to the 90% range, but it's getting closer. What's happening here? ERVs and dehumidifiers. That's what's happening here. Okay. But without them, when we cheap out, I call that a half measure. If you ask me, When you cheap out on this stuff, man, what you end up doing is you end up bringing all that insulation brings the temperature load down, right? All those better windows brings the temperature load down. Making the building tighter brings the temperature and the moisture removal down. But what happens when you get the building to a certain level of tightness? Well, you have to bring in the ventilation. And if you bring in that ventilation, you don't treat the air. You don't do anything with an ERV or an HRV or a ventilating dehumidifier or anything. You just bring in the outside air. Well, that load stops dropping. Okay, now some good things can happen with it, and we'll talk about those toward the end. But it stops, right? It was falling, and now we're just rerouting it, and it stops falling. But we're still improving the insulation, we're still improving the windows, we're still improving all this other stuff, which keeps shrinking that sensible load without shrinking the latent load. This is our unintended consequence. This is our problem. And it becomes a bigger problem if you start looking at loads on their peak humidity days, right? When you look at Austin, Texas, you can look up on ASHRAE's weather database and weather TMY data. You can find what the most humid day is, right? And on the most humid day, right, this ratio that I've put on here is what is the percentage of the total load on the design day if you looked at the total load on a peak humidity day, right? And so what this number means is this old school building stuff. This was 0.78 to 0.8, right? Call that 0.79, right? Is 79% of the load on a peak day, right? So you design on your hot day. What happens when the very humid day comes around? It's a little cooler. How much cooler? Well, cool enough that it's about 80% of what your peak load was, right? Which means your system is going to run 20% less on a day that you need it to run a lot. Okay. This is what it used to be. Look at where it is now. Yeah. This is a big problem, right? Because we've done such a good job of controlling temperature that when we lower that delta T, we really hammer that load down. And because as a percentage of where's the load coming from? In here, the load was coming from walls and ceilings and floors and windows and some infiltration, right? Where's our load coming from now, right? A lot of it is coming from that ventilation and infiltration, right? Particularly the ventilation, a higher percentage of it than was coming in before. And so what happens on that cooler, high humidity day is the runtime of the air conditioner falls further. Right? That's going to be a problem, right? Okay. So if we compare these things, right? If we compare the design peak to the humidity peak, right? And we look at the sensibles and just the sensibles. Okay. This was looking at the total loads. Okay. That means a big latent load was, I counted that in this one, right? So this looked bad, but here's the thing. The box on the wall, that's a thermostat. And the thing that tells the air conditioner run senses temperature. That's what it does. So really, it doesn't actually matter what the latent load is. When you want to look at run times, it's what the sensible load is, right? And so my design sensible load on my design day compared to the total load on a hot day was 90%. We've established that, right? It's in the 90% range, right? So I should get on a design day, on a hot day, I should get plenty of runtime, right? Even in our quote unquote problem area, right? I've only lost, a couple of percentage points here, right? I'm getting good runtime when I'm on a hot day. What happens on a cool day? Well, back in the day, it fell kind of a lot, right? It fell 60 to 62% of what we needed, right? And so that's going to be a big drop in system runtime. Look at what it falls to now, right? It falls to almost half of what we actually need. The temperature control needs on that peak humidity day fall like a rock, like a brick. And so even though I have even though this tells me I have too much capacity and it looks like a pretty big problem, what I have is way too much capacity relative to the temperature control needs, it's a much bigger problem than we think, right? That air conditioner on a day that we hopefully would have it running all the time, because it's the most humid day of the year, it's going to run a little over half the time. Yeah, that's a problem. And that's if it's not oversized, right?
Oh, it's oversized.
Oh yeah, I know it's oversized.
We know that.
Well, and even if it's not by code oversized, it's still oversized because we don't undersize equipment, right? So even if it's within the range, 15% oversized is not considered a problem sizing, but there's going to be an additional 15% on top of whatever we were looking at there. Okay, so the numbers we've been looking at are real numbers, right? I took a very common footprint of a home, put in a very common ratio of the windows, used typical building materials, etc. Right? It's not exactly a huge sample size, but at least it was based on real calculated data. This is just made up. Okay. And I want to put all my cards on the table if I'm going to do something like this. This is a brazenly fabricated data. But if you ask somebody, and you're asking me, what has happened to modern high efficiency equipment, particularly at the cheaper end of high efficiency equipment, is that if you look at the actual performance data, they spend newer, modern, more efficient pieces of equipment spend less of their energy on moisture removal and more of their energy on temperature control. It is pretty difficult to actually find a unit out there that's got below 80% sensible heat ratios, that spends more than 20% of its energy controlling moisture. Whereas it was a lot easier to find that stuff back in the day, because low efficiency systems, you could get colder faster, right? R22 systems with small coils got colder faster than modern systems. And so there has been a drop. I have made this particular data point up, but as this number drops, the relationship to what the ratio needs to be on our peak humidity days, like we were actually doing okay here, and this sort of became a problem, and now we're in big old trouble here. Okay, so the lesson here is, I'm not saying we should not make our buildings more efficient, but we are making it harder and harder and harder and harder to remove moisture when we improve the efficiency and don't introduce some sort of dedicated or supplementary dehumidification. If you're going to run on, or if you're going to rely on runtime and you're going to shrink your sensible load, that's going to be a problem, right? One of the things I'll often tell people is to think of sensible loads as reheat. Right now, I don't know if you guys know enough about the HVAC. Probably not all of us do, but when we have commercial systems where humidity is an issue, we have a heat source, right? We have probably in Texas, probably electric strip heat that's going to run in the supply plenum of an air conditioner, right? Why does it do that? Because it needs to increase the run cycles in order to get that moisture out of the air, right? So we'll cool the air down, then we'll heat it back up, right? What's that do? Well, we'll cool the air down, remove the moisture, and then warm it back up. We don't warm it all the way back up, but we warm it back up. Well, we're not doing that in residential systems yet. And I don't see us doing it because it's obviously not a very efficient way to do things. That having been said, we're in a situation where efficiency is starting to battle comfort and maybe even health. And so we are going to, I think, in the coming years, going to have to start to make some sacrifices when it comes to this stuff. So one of the things I did not capture with this analysis, by the way, I did not do manual S calculations on everything. And that's kind of a big deal because when you have outside air, this also can get a little complicated, but when you have outside air that's being drawn directly into the return air plenum, you have a higher concentration of moisture in that return air plenum, right? What does that do? Well, it means the air you're blowing across the coil is more humid than it would be that if you dumped it into the house through infiltration. And because it's more humid, you can remove more humidity from it, right? So things aren't quite as bad as I was showing on the page there, but it was when we were doing exhaust only ventilation, right? It's really quite a good thing that we've started to bring our outside air into that return plenum, because it increases the concentration of moisture and makes my unit more efficient at removing said moisture when it's running. Okay, so why does this all matter? Why is this all important? Well, I've hinted at it already. The data we use to size equipment, when you're doing it right, it's not AHRI data, by the way. There's another presentation, it's probably still on Spear's website, that I did on Manual S that talks about this. You don't use AHRI data. AHRI data does not capture the actual performance of a system. But when you do look at the actual performance of the system, and you have your sensible and latent loads broken out, that's for a full hour of runtime, right? That's the unit kicking on, running, and then kicking off. Well, in a partial run cycle, that it doesn't run for the full hour, what do you suppose our sensible and latent total numbers are going to be, right? 12,000, 25,000, 8,000, 33,000, right? We'd expect what, 12,500, 4,000, right? Whatever half of 33,000 is. And I'm not going to math them. Was that 16,500, I guess? All right. Once again, brazenly fabricated data here, made up. These numbers, that's because they don't publish these numbers. The stuff is not available.
I bet you those are pretty doggone accurate, though. Because
they're in the right.
I talk this all the time. How long does it take that coil to be running before the moisture starts to accumulate, drip, and remove itself from the hole?
That's right. Right. So it's that does not, that 8,000 does not become 4,000, becomes 2,500. Right. And there's a slide explaining this. Right. That first, I'm calling it 15 minutes, call it whatever you want. Depends on the unit. Actually starts off, it's doing literally zero humidity control, man. Nothing. It's just not cold enough. And then there's a point where it hasn't reached its target temperature, where it starts to do a little humidity control. Right. And then the humidity control kicks in. So we have these bigger surface area coils, right? That's why is that, why do we do that? We're making it up on the back end is what we're doing. Right. That hour of run cycle is doing more humidity control on the back 9, if you will, than it is on the front 9, right? Or at least on the, on the front 5 or so. So this is our problem. And the run fraction is all about percentages, right? If you're 100% oversized, you can expect it on a design day, on a hot day, to run about half the time. Right. And so this is a significant problem. So there's another problem coming down the pipeline, even if you are doing it right. And I mean, you're doing your best. Right. And I'm speaking from experience here. I spent some time recently doing a whole lot of residential designs in humid climates. And what you find, and what I already knew, I mean, I've helped people do these designs for years and years and years. But, I was put in the driver's seat to find solutions to these problems, and sometimes wasn't able to find any that weren't full blown, go buy a dehumidifier kind of solutions. And it's because of what I like to call the black holes, right? The number of BTUs is not what I'm worried about. It's the percentage. Okay. I don't care if you're 2,000 BTUs over or 10,000 BTUs over. If 2,000 BTUs is half the load on a mini split, that's terrible, right? If 10,000 BTUs is a small fraction of the load on a 5-ton unit or a big commercial unit, who cares, right? It's not about the BTUs, it's about the percentage. And we got a problem there, because these are the nominal sizes that we use in the HVAC industry, right? They got a 1.5, we got a 2, a 2.5, a 3, 3.5, 4, and a 5, right? Otherwise known as 18,000, 24,000, 30,000, 36,000, 42,000, 48,000, 60,000. Are these units exactly those BTUs? Oh, hell no. But these are the targets that the manufacturers use. And when they are off of these targets, they tend to be off of these targets on a fairly consistent basis, right? A modern 3-ton air conditioner in a particular climate is from all angles, it's going to be usually in the same ballpark of BTUs, even from multiple manufacturers. So what's the problem here? Why is this such a big deal? Well, The manual S tells me that I should try to be within 15% of my load when I size the system, right? Black holes, baby. Between 18,000 and 24,000, the gap is 33%. So what happens when your load is too small for a 1.5 ton? Too large for a 1.5 ton. What happens when the load's 19,000 BTUs and falls right there? 2 tons too big. 1.5 is too small. What are you gonna do? I don't have a great answer for this, guys. It sucks.
I do. Slightly improve your building thermal envelope because you
There
found
you
all
go.
this out during design.
Yes. Yep. That is the way to do it. Unless you're on the other side of 18,000, which is where I found myself all summer last year. We were already at a 1.5 tons. We couldn't, making it better wasn't going to help. And I couldn't tell them to make it worse. Townhomes, by the way, that's where you get bit right in the rear end.
Right.
Center unit townhomes facing north-south. Yeah, they're a nightmare. And you got to convince the builder to buy exotic, full-size air handler, 9,000 BTU mini split equipment, which they ended up doing, but is not an easy sell. Or you go with one of these 1.5 ton inverters and some dehumidification, which was another solution we found. But here's the problem, man. I am the HVAC contractor. I'm the HVAC designer. And I now have to convince my builder that they need to improve their envelope so we can justify the equipment size. And it's not a thing they ever had to do before. I'm almost sympathetic. I'm not, right? It makes me mad, but I'm almost sympathetic because it's like, why didn't I ever have to do this before? And it's because most systems were here, right? And when most systems were here, there wasn't gaps, right? There's this itty bitty little one. You can close that gap with airflow. You can adjust your CFM, right? And there's one here, but it's not, again, adjust your airflow, play around with some coil matches, and you can usually close that gap. And here, we're so large that the airflow ranges actually overlap between 4 ton and 5 ton. So you can get huge swings in capacity just by manipulating some of the things you have control over. But down here, we got problems, right? If you, so the 5 ton problem, it's not like if 4 ton CFM is 1,400 to 1,800 and 5 ton CFM is 1,750 to 2,250, assuming 350 to 450 per ton, you actually have an overlap here. So closing this gap really isn't very hard. But this is what nominal capacities would look like if we took 15% seriously. Okay. If the actual HVAC industry was designed around this 15% rule, it would be 18,000. 21,000 would be pretty close to a 15% bump, then 24,000. So that'd be a 1 3/4 ton, right? And you get rid of a 30,000 and instead have a 28 and a 32. And funny enough, do the actual math, 36, 42, 48, 60. 15%, if you're willing to round 1,000 BTUs or so, just to get it nice round numbers, this is where 15% works like a dream. And considering where the typical cooling system was when we started doing air conditioner, is it any wonder that this side of the spectrum works really good, right? This side of the spectrum used to be for exotic stuff. Now it's every day. The industry itself has a little bit of a problem. People love to blame HVAC contractors for like all of the problems that we have with building science. I sat at a meeting in building science summer camp where somebody just went on for like 2 hours. I don't think it was 2. I felt like 2 hours just saying how bad HVAC contractors are. Man, we are not giving them the tools to succeed, right? Because if we wanted to try to put, like, if we had a big house, we want to try to put a 5 ton in there instead of splitting it up into smaller systems, because those 5 tons are, we got more control over the, what the percentage is. Forget about it. You can't make 5 ton systems work, right? The late great Jack Rise, who is the HVAC design guru for the ACCA, the main trainer for ACA. His job is now being done by a gentleman by the name of Ed Janowski, who's also very good at what he does. But Jack is big shoes to fill. He used to go around the country before any of this nonsense, right? We're talking 20 years ago. I took my first class from Jack. He was going around the country saying 5-ton systems don't work, right? Why don't the 5-ton systems work, right? Well, because you've got to get that air to go 2 or 3 times as far through twice as many fittings with velocities that are twice as high as they are in a 2.5 ton. Everything is more restrictive. When he says 5-ton systems don't work, it doesn't mean that they all fail and need to be replaced. He means you're not getting the capacity out of them that you think you are, like, ever, right? And so when we have a house like this, we are better off splitting it up into smaller systems. Unfortunately, it can put us in those little black hole areas, right? Well, and hold on, we're going to get to inverters. I see that little that comment in there. We're going to get to inverters. They can help, or they might not. We'll see. So we're not going to talk about this very much. But in colder climates, we have situations where the heating load is falling way faster than the cooling load. And in terms of the furnace matchups, actually, this kind of does affect you because for whatever reason, you are very clearly heat pump climate, in my opinion. Is obsessed with using gas furnaces. And that's not great. And we'll see why that is in a little bit. But the fan size options that you have with that stuff is problematic at best. All right. So this is that bystander effect, right? This is, I like to say, generals are always fighting the last war. It's why we don't have a 1-ton air conditioner. Right, is because we've got to, this has got to be a big enough problem for somebody to go out and solve it. So we're going to have by the way, I'm guessing current constant mold issues and things that are starting to happen. I'll bet. I have some knowledge of that. I know they are. These problems are getting worse, and somebody's going to have to finally point out why before, and that's going to have to become common knowledge for to motivate these businesses to make the equipment that we need. Not all of them, by the way. Some of them are doing some pretty cool stuff along these lines. And it should be noted, I do know of 2 major manufacturers who are planning on rolling out a 1-ton model, and supply chain issues scuttled that. So before we demonize the manufacturers, which I kind of like to do, it's fun, right? Big corporations, they're easy targets. There have been some issues in the quest to do that. Yeah. And the other reason, by the way, guys, so like, if this is such a big problem, why isn't everybody trying to solve it? Because depending on who you ask, and I only had data from 2019, but depending on who you ask, for every 1 air conditioner sold in new construction, they sell between 6 and 7 in the AOR market, right? And so no wonder they're fighting the last war. They're still fighting the last war, for crying out loud. This is a very small percentage of the equipment being sold, being put in homes that have these problems.
And that's not changing anytime soon.
No, why would it? Right.
Yeah.
It's getting worse, right? We have a housing shortage.
Yeah. Wow. Yeah. I never even thought about that aspect of it. I mean,
and
most of their stuff is replacement, not new construction. Yeah.
Yep. So why don't they make that big, that low fire, big fan combo? Because it could only be sold in the new construction market, and that's real small compared to the rest of their market. Especially when you consider some of these brands sell most of their equipment in the AOR market, right? Some brands do a bigger chunk of their sales into new construction, and some brands do a lot less. So this is on average of the whole industry, right? But it's a pretty decent size issue there. So let's talk inverter for a second. Let's talk about our variable capacity equipment. So first of all, I call this miracle data, and I probably shouldn't. It is getting more commonplace to find this type of data. What type of data? Data from multiple speeds or multiple capacities of that equipment. I don't like the word speed, because even though it is accurate, it's confusing, right? Particularly for people who are only ankle deep in the HVAC industry, right? Because it becomes very difficult to distinguish between variable speed indoor and variable speed outdoor. Okay. So I almost always say variable capacity. Okay. What we're talking about here is inverter or multi-stage, like three-phase, right? Some of the five-stage stuff isn't technically inverter, and even some two-stage stuff. Getting data for the low stage used to be impossible. They just didn't have it. You'd ask and they'd be like, yeah, we don't publish that. Like, well, do you have it? No, not really. Okay. The hell am I supposed to do with this then? Well, you're supposed to size off the high stage. All right. But you've got people out here banging the drum saying the solution to all our problems is load matching, right? Meaning as the load goes down, the capacity of the equipment goes down, because that's going to give you long run times. And yes, it will give you long run times, but will it give you the moisture removal needs or meet the moisture removal needs of your home? That's a different question, because everybody's playing the damned SEER game. And compressors are expensive to run and fans are cheap to run. And so if I chose to design my new inverter system or multi-stage system to squeeze a little more energy out of the unit by running a faster fan, right? So that the reduction in power went down on the compressor faster than it went down on the fan, right? So if I ran everything at 100% at full capacity, and then at let's say low capacity, I was running the compressor at 50%, but I was running the fan at 60% or 65%. What would that do for me? Well, in the SEER testing, it would tell me that this has a higher SEER rating. The EER wouldn't be helped, but the SEER rating would. And everybody wants a big SEER rating. And so they design these things to do that. And so what happens, by the way, you also aren't changing the size of the coil as you reduce this capacity, which that surface area is absorbing heat very quickly because it's oversized for what its needs are, which means it takes longer for it to get really cold. So even if you didn't game the SEER game, right, you would still have a little bit of this effect, because what this is high stage and low stage. And if you look at the total capacity, it falls pretty steadily. If you look at the sensible capacity, it falls less. These are further apart than these are. This slope is lower. And if you look at the latent capacity, it falls more steeply. What are these bars? These are the sensible heat factors. Sensible heat ratios of the equipment. At top speed, this unit is almost a 0.7. It's a little over 0.75, which is really good, actually. I never tell anybody who this is because I don't want to discourage manufacturers from publishing this data. So I don't want to be out there banging the drum once they finally publish it to tell people how terrible everything is, right? Because these guys are no worse than anybody else, and they might be a little better, right? Because at least I have their data. But as it ramps down, now I've got, 0.78, right? Now I've got a little close to 0.8. Now I'm getting 0.83, right? But by the time I'm at the end, I only have about 10, 12% of my system's capacity controlling moisture at low stage. So the more it ramps down and the more it load matches, the less moisture removal it's doing. Guys, I know systems that by the time they get about here, right, by the time they get to about 65% capacity, have a latent removal of 0.
Well, now you always hear variable speed. They're going to run on low stage, but run longer. And by running longer, it removes more moisture. But this
not if the evaporator's too warm.
Yeah. Wow. See, I never thought about the law of unintended consequences like this. Well done, sir.
Yepper. And so there are units out there. I like to say if your mini split or inverter or whatever the heck it is, your multi-stage unit has a little water droplet on the control, you're probably all right, because that is a mode they can put it in. that will not float the temperature of the evaporator to a warm temperature. It will slow the fan down relative to the outdoor unit and will do a better job of moisture removal as it ramps down. But running in standard mode, and some of the cheap ones only run in standard mode, and they're completely algorithmically controlled by the brains of the unit. And there's no adjusting it on the controls. Once you're screwed, you're screwed. That's probably not great for the YouTube video. Sorry, folks. You are actually, you think you're making this, by the way, this is the problem with rule of thumb thinking, right?
Right.
You gotta, I have another presentation. The entire theme of the presentation is look it up, right? I don't care what it is, look it up, right? And so, and to make matters worse, like this is the multi-stage data for most manufacturers. It's, yeah, we're not telling. Forget you. So I won't tell you what this means, but if anybody wants to guess, I would love in the Q&A at the end to find out if anybody can guess what this little code means.
Science is so I got a good guess anyway.
Yeah, you probably do. This isn't my field of expertise. Indoor air quality is not my wheelhouse. I'm more about load calculations and whatnot. But we know that there's good ways and bad ways to bring in outside air, right? We know exhaust only, particularly in your climate, is terrible, right? You're going to backdraft a water heater. You're going to bring in humid air in all these places that are cold and cause condensation. Supply only, particularly in cold climates, can be just as bad because you create pressurization and you push that cold air, or in our case, you push the warm, humid air out, and it encounters cold surfaces and causes condensation. Balanced is better, right? But you ever seen this one, right? So the homeowner has this really big house and they don't want to put one big 5-ton system in, which is good. That's a bad idea. And so what are we going to do? We're going to bring in 3 2-ton systems instead, right? And what we're going to do is we're going to bring in all of our outside air onto one of these poor little systems. And so I've got 5 tons of outside air going onto a 2-ton unit. And you can absolutely, right? This is Chicago, not Austin, but in Chicago, 80% of the load coming in on that outside air is moisture. Only 20% is sensible, right? You can 100% just overload this thing to the point where it's not being able to keep up with the humidity. And the zone that's being served by this unit just becomes humid, because you should spread that outside air out. But technically I meet the code when I do this in my big house, and it's a bad idea. So one of the things we get when we tighten up our homes is the old Coke bottle effect, right? We deal with this more and more these days, right? You close the bedroom door and no air comes out of the supply. Now that was a thing before, but it got worse, because it used to be you close the door and air would just push itself out the window, right? Push itself out all the cracks and penetrations. That wasn't a good thing, by the way. It put a negative pressure on the home and sucked in air in all kinds of other places. But it was nighttime and the load wasn't crazy high, and we had low sensible heat ratio equipment. And so people didn't really notice. They woke up in the morning and they went downstairs. It was a little more humid than they were used to, but we got air into our bedrooms. Then we sealed the thing up like a Coke bottle. We try to blow air in, it's not going to go in. Right? You can't compress the air in a room. So we get this crazy idea. I know we're going to solve this problem by having more returns. We're going to have return air in our bedrooms. Now, Dr. Bales entirely stole my thunder on this one. He just wrote an article. I was creating this presentation when that thing got published about how single returns are better than multiple returns. As Dr. Bales likes to say, I explain things like an English major. He explains things like a PhD candidate. So maybe I'll do a decent job here. So this is why we call it Wack-A-Mole, by the way. I'm going to fix the room pressure problem. Now I'm going to cause a duct pressure problem. Why? So you guys are in Texas, and this is great because a lot of your return systems are all home runs, and that's actually not nearly as bad as the trunk and branch stuff. On trunk and branch stuff, you get supply air. So this supplier wants to go through the trunk, okay? And as it passes these takeoffs, there's a little bit of a swirl in the air right here. So the air going through gets a little bit of resistance, but not much, right? Because this air gets out of the way and this air keeps going. In the return, you have a T-bone collision. every time this air comes into that trunk, right? And so I used to work with the guys. I used to work for the same company as M&M Sheet Metal. And I know the guys over there and Chris Van Wright and all those folks. And I love sheet metal. Sheet metal's great. Smoother, it's better, it's easy, it's harder to F it up. That having been said, on a return system, you make your, I don't care if this is round or rectangle, you make your return look like this, it is going to be more restrictive, particularly when you bring the bigger amounts of air in to these to the air volume. If this is a bigger air volume than this, it won't resist as much, right? Because this will push its way in and it'll just pull the air around. Excuse me, if this is a smaller air volume than this, the smaller the air volume is going in, the less it disrupts the flow of air. The bigger the air volume going in, the more it disrupts the flow of air. And it just so happens that the bedrooms are always the far ones away. The bedrooms are always the ones with the little ones, and they come in at the end, and the big one is always near the unit, and it disrupts the flow of air big time. And so you get these giant pressure losses and these giant resistances on these trunk and branch systems, right? So people make fun of, and I'm not a big fan of junction boxes in general, right? I'd rather see Ys and other things, but people make fun of flex systems in the snobbier northern climates. But resistance adds in series, not in parallel, right? Think about low voltage wiring. If I bring everything into a single point, there's only one place where I can get that restriction instead of adding it up 5 times throughout my duct system, right? So this is one of the annoying ones. So you make things better for newer, more efficient homes. We can end up making things worse for older, less efficient homes. This is one of my favorite. If the DOE is right and half of all systems are oversized, right? That means that, my air conditioner is too big and my ductwork's too small. And what does that do? It actually balances out and makes it work. So why? It's because, not enough airflow is reducing the capacity of the unit. It's also increasing runtime because the capacity is lower, and it increases humidity control. Less air across the coil, more time in contact with the coil. So I get more moisture removal. The coil gets colder faster because I'm not dumping as much energy into it. It's a win all around, except for efficiency, right? So we replace that old split capacitor motor with an ECM. What happens? Well, I probably get more airflow. Not a good thing in this case. I was relying on reduced airflow to maintain comfort. I also start using a lot more electricity, right? A split capacitor motor under high load uses fewer amps. A constant torque motor under higher load uses more of them, right? And so when you start, when you start doing this, you get worse performance overall, right? And one of my favorite ones is when you go in an air seal, a leaky duct system. Cool. All that air leakage, you know what that's called? Pressure relief. It's not a good thing. I don't want it, right? Remember the very first slide. I'm not advocating leaky duct systems, but you go in and seal them up and you don't look at the duct sizes and you don't look at the amount of airflow you're putting into it. You're going to increase the static pressure on your fan, and that can have some huge negative consequences. Okay. So I'm going to skip that slide because that's the slide where I apologize to a room full of HVAC people if they already know this. But my new saying here is the rule of thumb is broken, right? The thumb is broken. If you compare loads, right? Your heating loads are like 3 times or 1/3 what they used to be. Cooling loads used to be 2.5 times what they are now, right? And then we talk about ductwork and people are still saying a ton is still a ton. And go watch that. I know the title of this one. It's there's no such thing as a ton. I did it for Jason and you guys a couple of years ago. But this is where you get the same. You get a lower load. You get the same air volume. You get less airflow. What are some of the negative consequences of that? What is the negative consequence of making the building the same size but the air conditioner a lot smaller? Well, one of them is filter effectiveness. We don't really think about this, but we used to cycle the air through that filter, the whole volume of air in the house. If this was 2000 CF, we'd cycle the air through the filter 5-6 times. New modern house with a much lower airflow, twice. That filter is not being as active at removing particles from the air, right? No wonder we say we want more outside air in here, right? Because the filter isn't cutting it, right? We do those air metering to indoor air quality meters, and we find that things aren't great. This is one of the reasons. So to be fair, infiltration is often, not always, bringing in lower quality air. So tightening the building is stopping some of that low quality air from getting inside the house. Sometimes it's not such low quality air. Sometimes the call is coming from inside the house. Sometimes those VOCs are off gassing from cleaning products and things inside the house. And this is actually not a bad thing. So also, and this is one, that whole, we were talking about like the watts per CFM thing. We're gonna have to keep an eye on that as an industry. We're starting to set unrealistic standards, right? Don't look too closely at this because it doesn't make physical sense. It's MC Escher's duct system, but shorter duct runs, my 3D drawing skills in PowerPoint are somewhat limited. But shorter duct runs for the same amount of air means it's easier to move that air. Longer duct runs means it's harder to move that air. That means all things being equal, that fan has to work harder, which means we are asking fans to be more efficient while they do more. That's not an easy thing to pull off. Okay. So, you know, you could make it a 7-inch and that'll be better, right? That's good. The other thing that we lose when we have a bigger volume and lower airflow is air mixing. Right. And so back when we were putting 90 CFM in this room, we'd throw the air 16 feet, right? It'd be 700 feet per minute. Now, if I'm going to use the same 10x6 grill, but I'm only going to have 60 CFM coming out of it because, you know, that's 10x6. That's what goes in a bedroom. Now I'm only throwing the air 10 feet. Doesn't go as far. It doesn't get to the outside perimeter of the building. Less important that it does, by the way. But this 400 feet per minute's a problem. That seriously causes air stagnation. So what we actually need to do in this space is put an 8x4 in there. Well, they don't sell that in the supply house. And I also need to put the same size duct to it. So I'm not, that 8x4, it doesn't go on a 4-inch duct. It's going on a 6, right? And they don't make a boot like that, right? So now I got to use an increaser to make it fit, or a reducer to make it fit, or whatever it is. And I have to listen to distributors and HVAC contractors argue about, well, we would stock it if you bought it and we would buy it if you stocked it, right? So another one that I like to point out is we're trying to make everything more efficient. We don't want to make it more expensive. When the manufacturers say they've managed to do that, I call that a red flag. If you dig deeper into the data, you can usually find some problems. This is airflow. So this is a color-coded nightmare. I need to fix this slide. I apologize. Don't try to look at it and glean anything useful from it. If you have the time to look it over, it can tell you useful things. This color code is how many useful speeds there are to get the amount of airflow you need at 1.5, 2, in between, 2.5, 3, and in between. Because this blower, this is one of the most commonly sold furnaces on the face of the planet. Family of furnaces sold on the face of the planet. There's actually 1, 2, 3, 4 different furnaces that you can get that uses a 3-ton drive. And they use that 3-ton drive for 1.5, 2, 2.5, 3, right? They use it for all of those sizes. And so if you need 525 CFM, why would you need 525? I thought you were doing 400 CFM per ton. Well, if the latency's going up, you better slow your air down. More air. We used to think of more air as a good thing. Now, oh, you got more air. Who cares? More air is good. Now, well, more air reduces the moisture removal capabilities of your unit. I want less air. I want exactly the amount of air that I want to have. And when all of the furnaces available from this family of equipment, from this brand, out of all of them, there are only 3 capable of it. And on 2 of them, at only 1 static pressure and 1 fan speed, where I can even get close to this, that's a problem, right? What happens if I need the 60,000? You don't, you're in Texas, so don't worry about that. But what would happen if I needed this one and had a duct system that was large and was going to have, 0.5 or 0.6 inches of static pressure? 0.4 isn't a whole lot. That's not a very powerful fan, right? And, so here's another option, right? If I want 875 CFM, right? I hope you're using the 60,000 wide, because anything else is going to be operating at 0.7 inches of static pressure. Jason, that conversation we were having about watts per CFM, what do you think that does to that? Right? That is not good. No. Right? So, as we improve our efficiency, right? The pitfalls of manual S. How about the new coils we're using? Anybody ever looked up the pressure loss numbers on them? Right? I did. So the old coil that we were using for the standard for high efficiency, right? I'm not talking 20 years old. I'm talking last year, right? The old coil from last year had a pressure drop of at a 3-ton at 1200 CFM, had a pressure drop of 0.28 when it was wet. The new equivalent coil that's going to work with SEER 2, 0.36. That's a 30% increase in restriction. Not good. Unintended consequences, man. So the folks over at HVACR school have this saying. They didn't make it up, but they have claimed it as their own, and I can't blame them for that. That's great. The RTFM, you guess what goes there. They call it fantastic manual. Look it up, do the math, whatever you want to call it. My sort of reminder to everybody is it's great that it's working now, but if you don't know why it works now, you're not going to know why it stops working later. When they pull the rug out from under you, and it's just nothing but rug pulls in the last 10 years. When they pull the rug out from under you, you can understand why it's working now and anticipate what's going to happen, or you can put in 10 of them and have a bunch of things go wrong and figure out the problem is. I'd rather do the first. All right. Let's see.
Yeah. Well,
I'm reading some of the comments and questions while
from HVACR school has been ignoring me for a couple of years. He's not as willing to donate an hour of his time as you are. So
I know what that guy's schedule looks like. I got more time. Not to make excuses for him, but man, oh man, he's running a full-size HVAC business while he does all the other stuff. Like that's
well, he has to be making 3 times the money through his YouTube, does he not? I mean, he's got hundreds of thousands.
He's probably doing all right. He's probably doing all right, but like there ain't a lot of time on his schedule. Even when he's got a dedicated event, it's hard to. I gotta get dinner with the guy just to have a more than a 5-minute conversation with him.
But the biggest thing I learned from that presentation, now granted, I will do it in a lot smaller font that blends in with the background, but I'm just going to, my next presentation that I put together, I'm going to have asterisks everywhere with brazenly fabricated data. I love it.
Well, it's only because it's unavailable to anybody who wants it, who doesn't work for the manufacturer. I would happily use non-manufacturing data, but I can't get it. If anybody knows of a study, I know FSEC did some looking into it, but it had a sample size of like 4 different units. Like that's not a lot. Yeah. It drew the same conclusion, by the way, but I wouldn't call that a longitudinal study or anything like that. It's but they did look at it, right? And drew similar conclusions.
And if anybody needs to hop off, we are at our hour. So no worries. Sorry, if you need to hop off, but I do have a few questions and feel free to go ahead and type in some more.
Absolutely.
Just in general, Alex, what would you, so I assume you're familiar with the CFM outdoor air ventilation rate requirements in the IRC.
ASHRAE 62.
Yeah. In my mind, those are based on worst case scenario, little old couple, 9 cats, 3 dogs, don't open a window. What are your just general impression on those rates?
And I'll tell you what, I'm going to tell you guys what the weird symbology was here. This is Mean HVAC is nowhere near as good as Allison Bales. That's his bolo tie.
I wasn't going to get that.
It's a dumb, weird joke. That's a question for my bettors.
Speaking of people I couldn't get to donate an hour, there's
I don't doubt it, right? So the Joe Steebrooks, the Allison Bales of the world know a little bit more about indoor air quality. I'll tell you what, maybe even somebody like John Ellis, who's an IAQ expert. Little bit out of your wheelhouse, but might be a little easier to get. I have trouble with the underlying premise of you need a certain amount of outside air in the building. Like any code is going to be really sloppy, right? Yeah. Because you need as much outside air in your building as it takes to remove the VOC, remove or dilute the VOCs and the ppm 2.5 and all the rest, right? And my guess is that because they have a good answer to that question, I would have to have a huge sampling of homes with data loggers on indoor air quality over a long period of time before I would want to give that an answer. But I think a good ventilation system would be tied to an indoor air quality monitor.
Yeah.
Right.
And that's
give it as much as it needs and don't give it more, because giving it more is not good. Right.
No.
But giving it less when it needs it, also not good. Right. And so we are probably erring on the side of caution and trying to find a line in between. But, my favorite is, what if the outdoor air is lower quality than the indoor air?
Right.
Yeah. Mm-hmm. Why am I bringing outside air if if you're in Salt Lake City? All right. I know you guys are Texans, but Salt Lake City has some of the worst.
And those inversions are crazy. I've been there during one.
Yeah. The rainbows are pretty. The sunsets and the sunrises are pretty, but that air quality is awful. You might be better off trapping yourself in the house with no outside air. You might not. I don't know. But man, the quality of the air you're bringing in must have a lot to do with how it's affecting the indoor air quality. So, maybe CO2 monitors, maybe, some of these new IAQ monitors being tied to your outside air wouldn't necessarily be a bad thing.
I think it's in the next 2 code cycles. I think we see it, just because those IAQ, those monitor, or the controls, and they're just getting cheaper, and they're getting
more widely available, cheaper, easier to install,
and indoor air quality's getting worse. And so,
yes, agreed. Yeah. That new haven that goes into the return air plenum is a thing I'm considering putting in my house.
I haven't seen that haven.
It's kind of like, have you ever seen maybe you haven't. You're in Texas. You ever seen a steam humidifier for like winter applications? It's like this wand that goes into the supply plant.
When I go snow skiing.
Yeah. Okay. So it's kind of like that. It's a small thing. It's low profile, so it doesn't impede airflow very much. It's got a hot wire anemometer in it, and it's kind of like you drill a hole and you plug it in, kind of a thing. And it's because it's going into your return air plenum, it's you don't have to put them in 5 different rooms of your house.
Right. Yeah. No, that makes a lot of sense. And follow that up with, in your opinion, now granted, keeping in mind that money is an object, not no object.
Oh, hell yes. One of the things that drives me nuts about some of our building codes. Okay. You guys are energy people. I don't know who's sitting on these damn code committees. Let me build a smaller house without penalizing me, please.
No, it doesn't work.
Cube square law is a thing. It is so much easier to pass all of our energy codes on large houses than it is on small houses. Yeah. I am disincentivized to build a small house. God help you if you're in your 20s and you want to buy a house. Sorry.
Well, they
you touched a nerve, Jason.
No, I'm happy.
Sorry about that.
In the 2021 energy code, they adjust houses under 1,500 square feet. You can use 0.02 less CFM for your blower door calculations. They've tried to correct that.
That's a little bit of a sop, though. I mean, I'd rather see the overall ERI requirements change.
That's a good idea. Tie it to the ERI. Yeah,
that's just me.
Yeah. As long as I'm getting your opinions, in your opinion, again, cost being a factor. Yeah. Best ventilation system for Texas, for climate zone A, the humid climate zones, not West Texas.
Yeah, West Texas, you can get away with just outside air.
Yeah.
Look, we are well on our way to needing to decouple the jobs of temperature control and moisture removal. This trend, right? This trend, especially when you look at the peak humidity days, right? And this gap that you need to close. Yeah. If I'm anywhere on the Gulf Coast, give me a dehumidifier. Ventilating dehumidifier.
Just to me, anywhere on the Gulf Coast, code is the crummiest house you can build. To me, anywhere on the Gulf Coast, and I don't know where you would get the weather data, but in really humid areas, how supplemental dehumidification is not required by code boggles my mind.
Yeah. So if anybody's ever interested, the website that you go to get this weather data is ashray.medio.info/v2.0. If you literally Google ASHRAE weather map, you'll get this.
No, because I have, and that didn't come up.
All right, so try ASHRAE Medio, MET.
Okay.
Got it. METEO .info, and then this is v2.0 right there. You might want to put that in the old doobly-doo in the YouTube video.
Yes.
So if I'm going to go to, give me a place to. Am I going to Corpus? Am I going to Austin? Am I going to Houston? Where do you want? Galveston? Where do you want me to go?
Corpus.
All right, Corpus it is. Good choice. So what you do is you find your place on the map, and then it says just right click on any side of the map and we'll get the nearest weather station. So I right click on here and it pops up with all of the different. So I right click there. Here are all the different weather stations, right? So if I want to go to this one here in Corpus, I can just click on this.
It's that easy. Houston's been asking me. There's a couple of blanks in this chart. I actually sent you the email and you politely ignored me. But
Sorry.
There were a couple of blanks in this chart.
If you sent it to me in late 2021, I ignored everybody back then. I apologize.
No, hey,
there's a reason I'm out on my own.
Yourself. You have redeemed yourself 1,000 times over with this. This is exactly what I needed.
All right.
Fantastic.
So you right click on the map, you find your location, you click on the location. And what we normally do, so there's your annual cooling, dehumidification, and enthalpy design conditions. We usually use the cooling 1% data. That's our target design for a load calculation, right? So that's going to be the dry bulb and the mean coincidental wet bulb, right? So those are your design conditions on that 1% day right there. On the dehumidification side, your peak dehumidification day is usually people use I don't know who makes these rules, but it's the 0.4% day that you use for peak dehumidification. And so my dew point is 79.1 degrees, by the way. So anything colder than 79 degrees causes condensation. Yeah, that's a big deal. Your humidity ratio, which is the literal amount of moisture in the air, is 151 grains per pound. Is that humidity ratio? I think it is. It might be, can't be pounds per pound. It would be a smaller number. And so they do the mean coincidental dry bulb on this side. And so it's 83.3 degrees out on the most humid day. And the dew point is 79 degrees. And if you want to turn that into a dry bulb, wet bulb, you just use a psychrometric calculator. There's a bunch of free ones online. Just Google, free psychrometric calculator and off you go. And you can plug those numbers in, and you can take those design conditions and put it into a load calculation tool. It could be right off, could be a lead. I don't care. They let you plug in numbers. And that's how I did the analysis. That's how I looked this up and found what those numbers are.
Might not actually have what I need, but if it doesn't, I'll pester you again. What are your thoughts? Then the last question from me, as far as based on in Texas, so the difference between climate zone 2 and climate zone 3 in the energy code is light years. You go from 3 ACH to 5 ACH, so you've got a 40% tighter house. Yep. And you go from an R20 wall to an R13 wall, so a much crappier wall.
Yeah.
No. You
go to a better wall.
Well, yeah, a better wall. Yeah, from 2 to 3. So you go a tighter house, 40% tighter house, and almost that better wall. An R13 wall in climate zone 2 seems inadequate to me. What just general thoughts on heat losses through walls, and are they a weak enough point that an R13 baseline wall should be reconsidered for climate zone 2?
I don't think so, actually. No? Okay. And I'll show you why. Let's see. Do I have? That didn't do it. I've got a PowerPoint slide on this. And I'm having trouble finding it. Come on.
And we
R
still have
versus
70 people on just to listen to the show. That's
listen to me
awesome.
look for a stupid presentation.
No, I mean, that's
Oh
great.
boy. Oh boy. So let me just browse real quickly. So
No worries.
R value. No, R versus U, maybe. Oh, for crying out loud. So the relationship is inverse. Long story short. And when you map out here, actually, I can build the freaking thing. Oh, it might be in Excel, you dummy. I might have it right in here. Sorry, I don't like to show all of my recent files. It shows all my master machination. So you have to look at the blank page for a little bit. There it is.
It just seems crazy to me that right up, and it's just the difference between climate zone 2 and climate zone 3 in the energy code is so stark that the energy efficiency part of me is telling me that R13 wall is a problem.
So our value,
and particularly if we can get some continuous foam and stop the thermal bridging rather than just a 2x6 wall.
Again, that's not where our problem is.
No.
So let's see, class resources, son of a gun. Hey, there we are. Open, there we go. So that's how our value works. Let's zoom in. Once you hit R13, you see how flat this curve is?
For what? I mean, that would change based on the delta T though, right?
Nope. So this is what these numbers here are U values. These numbers here are R values. Okay. Yeah, R49, huge waste of money.
Well, how do you justify more than R19 in a ceiling?
And so, yes, delta T does matter because you take the small difference and you multiply it by the large delta, right? Yeah. But it's still a relatively small difference, right?
So going from 38 to 49, like the
going from 38 to 49, yeah. I mean, you can use this is definitely more in my comfort zone here, right? You take a building and
have a lot. I sit in a lot of these arguments as efficiency folks just want more and more insulation. You start doing the calculations and I've kind of found some of this same thing.
It's the law of diminishing returns, right?
Right.
I mean, so if I go
to the agreed upon right number, I guess then, because there's diminishing returns past R1. You know what I mean?
No, but that's early, and so it's and it's always going to be like economical. Why do we insulate the crap out of our attics? Because it's easy and cheap. That's why. Right, and so when you compare it to the cost and the difficulty to implement in a building, they're saying, well, let's just put extra insulation in there. Yes, I have to put 5 times the amount of insulation in my attic than I would in a wall to get the same benefit. But it's easier to put 5 times the amount of insulation in the attic and cheaper because I don't have to frame out my walls with thicker walls.
Right.
So if we look at our breakdown here and I take a look at my my ceiling, right, which is currently R50, on the cooling breakdown for this 44 by 30 foot room, little 1,300 square foot, footprint, the ceiling load is 1,500 BTUs. If it was R38, ceiling load would be 1,900 or 2,000 BTUs, 500 BTU difference.
Which that's on a percentage, that's pretty significant.
Compared to what I can get out of windows or compared to what I can get out of moving the ductwork inside the conditioned envelope.
Yeah, I mean, you need to think about the total UA. Absolutely. Right. I mean, yeah.
And so if we look at, and so you got more windows, right? I mean, more walls than ceiling area. So we can do the same thing to the walls, right?
Yeah.
So if I go from an R13 nothing wall, that's 3,000 BTUs of load in the cooling season, right? And if I bring that to R19, is that climate zone 3?
It's 20, but 19 is close enough.
All right. So I'll do 21. I'll do 21.
Why they make it 20 when they make insulation?
So that's a 1,300 BTU difference, right?
So that's super significant. I mean, it is and it isn't. I get, but I mean, on a percentage basis, it certainly is.
Dollar per BTU? No.
Dollar per BTU.
I disagree.
Yeah.
It costs a lot to go everything 2x6 and I'm not saying it's not worth it, but I mean, for 50, I can save 1,500 BTUs a lot of different ways, and that's an expensive way to do it.
Right. I guess if we did our weather resistant barrier and our roof and foundation, if we had all our other details correct in our home, and our home was going to last 150 plus years like it should, then some of these, that stucco home I showed you pictures of before we started the
that ain't lasting
presentation,
100 years.
that house ain't gonna last 40 years. So
Yeah.
it doesn't make any sense putting better walls in that house.
Well, and I'm not saying we shouldn't build the best building that we could, but we should be smart about how we spend our money. You clearly touched the nerve when we were talking about what what happens when young people without money are trying to build houses or buy houses these days. Yeah. Every improvement, prices, it makes it harder and harder for people to get a home. And while that's great, because we invest this money so that because if we all put the money in and we all make our homes more efficient, then we don't have to pay for new power plants and grid upgrades and potentially all of the catastrophic consequences of climate change, right? Yeah. But we should be smart about how we spend our money. And if I can still put commercial systems in that are 3 times oversized because, God forbid anybody, feel a 1 degree temperature difference in a building, and we can do all this just in case bullshit because an engineer stamped it. I'm going to tell the residential people to take it easy and maybe point the focus where it belongs. Hey, it's your fault. You gave me the soapbox. But if you look at this load, why don't we do something with that window load? Right. Think of it in terms of the pie chart. Like where's the meat on the bone? Right. It's right there. That's where my problem is. Right. And that ducts piece of pie, you can eliminate that. You can make it go away if you bring the ductwork inside the conditioned envelope.
Yeah.
Right. Like that's where I like to see those improvements. Plus, anytime you're next to one of the lines, it's going to make no sense because they're arbitrary. Anytime you got an arbitrary line, it's going to be you could stand with 1 foot on either side of it, and all of a sudden you need a different amount of insulation. It's never going to make sense if you frame it that way, because you have to have lines somewhere. Otherwise, because insulation values or insulation is only available in certain increments, right? Yeah. A gradient approach would make sense, but we can't have gradients of insulation, right? I can't have our 16 and a half in a wall, right? Like it's not an option. And so we can't slowly increase it. We just have to pick a line, go across it and say, from here on in, you're going to do it. And when you're close to that line, it probably doesn't make a whole lot of sense to be on either side of it. A blend of those things would probably make more sense, but it's hard to write codes that way, like really hard. Yeah. And then you're just going to draw more arbitrary lines. So it's not right. How many times do you want to split the difference? Right. Yeah. So, look, I'm all for building a better home, all for building a better envelope. I really am. But cost benefit analysis is well worth it. And like I said, build a smaller friggin' house.
Yeah, but I need a media room and a gym, and
I really
need all that stuff. Didn't need houses. I want a bigger house.
Yeah. Well, and you should be allowed to have a bigger house. Like I'm not saying mandate smaller homes. I am saying make it cheaper to build a smaller house. Right.
Yeah.
If I want to live in 1,200 square feet and, my buddy wants to live in 5,000 square feet, I don't know why I have to build my house to the same standards when it's harder on me to do that.
No,
because
of that is and that there are some Bozeman, Montana, off the top of my head. There are a handful of jurisdictions, especially jurisdictions that have the ultra wealth, where a 10,000 square foot house is a small one.
Yeah.
That are doing some things about that. Over X amount of square footage, you have to have 10 points better on your HER score or whatever it may be. That's a gradient HER score relative to the square footage. I think that's a great idea.
Yeah.
Awesome. Well, Alex, once again, you did a fantastic job. I cannot thank you enough for your time today. I'm going to hop on that ASHRAE website. Oh,
right.
will you send me a PDF of your slides, please, sir? I'm sure the folks would like it.
Yeah, I can do that.
And you make sure you have your contact information on there, and you might put a little blurb on there about training, what you offer with Meaney HVAC.
Yeah, I'll point people at the website.
Awesome.
Cool.
Well, thanks for joining us, everyone. And Alex, you are always welcome. You let me know when you get your next one ready, and you are more than welcome to try it out on me and get the kinks worked out before you take it to the full congregation, because it's always great.
All right. Well, thank you very much, guys. I hope you found the time well spent, and I will see you out there.
Awesome. Thanks again. Bye, everybody.
Bye, man.